Capacitors are just one of those fundamental components in electronics. The best way to think of them is like tiny, super fast charging batteries. But what happens when you need more juice, or maybe you need to handle a higher voltage than one little capacitor can take? Well, you team them up. The real question, though, is how does the way you arrange them change how they work? And how do we calculate what's really going on in that circuit?
Okay, here's what we're going to cover. We'll kick things off with the two main ways to combine capacitors. Then we'll crunch the numbers for each and see how that plays out with charging time. After that, we'll figure out how much energy they actually store and wrap it all up with the key things you absolutely need to remember.
So, first things first, let's get one fundamental idea straight. When you're building something, it's not enough to just throw some capacitors in there. The way you actually wire them together, that completely changes their overall ability to store an electrical charge. And that right there is the whole ball game. It isn't just about adding more parts to the pile. It's about being strategic. You're arranging them to get a specific result, whether that's more charge storage or the ability to handle way more voltage.
All right, let's jump into our first method, and honestly, this is the one that trips a lot of people up at first. It's when you connect capacitors end to end in one long chain. We call that connecting them in series. Logically, you'd think adding more capacitors means more capacity, right? Always. But here's the wild part. When you hook them up in series, the total capacitance actually goes down. In fact, here's the crazy rule. The total will always be less than the value of your smallest capacitor in the chain. So why on earth does this happen? Well, it all comes down to the math. To find the total, you don't just add the numbers up. You have to add their reciprocals. That's 1 divided by each capacitance value. It's this weird inverse relationship that makes the total value shrink. Let's just run through a quick example. Say we connect a 10 and a 220 microfarad capacitor in series. We start by adding their inverses. So 1 over 10 is 0.1, and 1 over 220 is about 0.0045. Add them together, and we get this intermediate number, 0.1045. But wait, and this is the step where everyone messes up, so listen close. That number we just got, that's not the answer. That's 1 divided by the answer. To get the actual total capacitance, we have to do one more thing. We gotta flip it. And bam, there it is. 1 divided by our number, 0.1045, gives us 9.56 microfarads. See, it works. Just like the rule said, our total of 9.56 is even smaller than our smallest 10 microfarad capacitor. Kind of cool, right? Okay, after all that tricky inverse math, you can breathe a sigh of relief. Our next method, connecting capacitors in parallel, is, well, it's just wonderfully straightforward. When you wire capacitors in parallel, each one gets connected to the exact same 2 points in the circuit. The best analogy I've ever heard is to imagine you're just adding more water tanks to a system, side by side. You're just giving yourself more total storage. And the math for this, it's exactly as easy as you'd hope it would be. You just add the values straight up. So for our 10, 220, and 100 microfarad capacitors, you just add them. 10 plus 220 plus 100 is 330 microfarads. No tricks, no flips. It's that simple. So here's the bottom line. You've got a choice, and there's a specific reason for each one. You use series when you need to handle higher voltages because that voltage gets spread out across all the capacitors. And you go with parallel when all you care about is getting more total storage capacity at the same voltage. Okay, so we know how to figure out the total capacitance. But so what? Why does any of this actually matter in a real circuit? Well, it all comes down to one thing: time. The capacitance dramatically changes how fast a circuit can charge up or discharge. Just take a look at this. When you connect a capacitor to power through a resistor, it doesn't just instantly fill up like a bucket. Nope. It charges along this really predictable, beautiful exponential curve. It starts off super fast, and then it slows down as it gets closer and closer to being full. And we can measure this charging speed with a really important value called the time constant. You'll see it represented by the Greek letter tau. This is the absolute secret to understanding charging behavior, and to find it, you just multiply the resistance R by the capacitance C.
So for this circuit we're looking at here, we multiply our 10,000 ohm resistor by the capacitor's value. But remember, it has to be in farads. So 100 microfarads becomes 0.0001 farads. And the result? A time constant of exactly 1 second. This one number unlocks everything. So what does that 1 second actually mean? It means that after 1 second, one time constant, our capacitor is about 63% charged. After 2 seconds, it's at 86%. After 3, 95%. The general rule of thumb that everyone in electronics uses is that it takes about 5 time constants, so 5 seconds for this circuit, to be considered fully charged.
Okay, so we know how to combine them, and we know how fast they charge. But how much, punch do they actually hold? Let's figure out how to measure the actual charge and energy we can get out of one of these things.
Now for this, we use 2 different formulas, and it's important not to mix them up. To find the total electrical charge, which we measure in coulombs, we just multiply capacitance by voltage. But to find the stored potential energy, measured in joules, that's the actual work it can do, we use a slightly different formula. 1/2 times the capacitance times the voltage squared. 2 different measurements for 2 different things. All right, let's wrap this up. If you remember anything from this, let it be these 4 key rules. In parallel, capacitance adds up, voltage stays the same. In series, capacitance goes down, but your voltage rating goes up. The time constant tau tells you everything about charging speed. And it always takes about 5 of those time constants to get to a full charge. And there you have it. Look, these formulas aren't just equations on a page. They're the real-world tools you need to build some really amazing things. So now that you know the rules, the only real question is, what are you going to build first? Are you going to make a precision timer, a high-voltage circuit, a massive high-capacity power bank? The choice is all yours.